Hi, I'm Craig Duguid and I'm going to talk a bit about my work on tidal flares. So tidal interactions are important for the spin and orbital evolution of short period planets and close binary stars. In both cases we observe that when the orbital period is less than 10 days we typically have circular orbits. We also find growing evidence for the inspiral of some hot Jupiters, in particular WASP 12b has some quite compelling evidence for this. So one important mechanism for this is the interaction between the large-scale non-wave-like equilibrium tide and convection. This interaction is thought to act as an effective viscosity in dampening the large-scale tidal flows, but the efficiency of this mechanism is somewhat debated, particularly as it's expected that the effective viscosity should be reduced when the tidal shear frequency is larger than the relevant convective frequency. But the debate is what this reduction should be. So from theoretical grounds, Zahn had predicted that the effective viscosity will go like 1 over the tidal frequency, whereas Goldreich and Nicholson proposed that the effective viscosity will go like 1 over the tidal frequency squared. People have done simulations, various groups, and have found agreement with both cases. My work has found agreement specifically with Goldreich and Nicholson. I'm going to talk a little bit about the mechanism behind the -2, but mostly I'm going to be focusing on a scaling that is different from all these proposed, from the -1 and the -2, and that also occurs for frequencies that are less than the convective frequency. So our approach has been to simulate a small patch of convection in a Cartesian domain using the well-studied Rayleigh-Benard convection equations under the Boussinesq approximation, using impermeable, stress-free and fixed temperature boundary conditions. We also decompose the velocity field in terms of a background shear flow U0 and everything else. This background shear flow is essentially our tidal-like shear flow. I say tidal-like because it's one component of the full tidal shear flow, but under the linear tides approximation we can sum these contributions together to get the total. Also it's tidal-like in respect to it's a local approximation for the global tidal flow. So the parameters of this that we're interested in for the purposes of this talk are the domain size, which will be Lx is going to be equal to Ly, but so when we vary one, we vary both. We're also interested in the strength of convection, which is parameterized by, in our case, the scaled Rayleigh number, which is the Rayleigh number divided by the critical Rayleigh number required for the onset of convection given our domain. And everything that we've got time to speak about in this presentation, the Prandtl number is going to be equal to 1. And there will be brief mention of the shear amplitude A0. So the thing that we're interested in is the effective viscosity. So we evaluate this by considering the mean rate at which shear does work on the flow and equating this to the mean rate at which energy is dissipated by viscosity. We equate these two things, we rearrange them, and we get this expression for the effective viscosity, which is a function of the shear frequency. So now let's consider some results of simulations in 3 different strengths of convection, twice critical, 100 times critical, and 1,000 times critical, where we've plotted the scaled effective viscosity as a function of the scaled shear frequency. We've scaled the shear frequency by the relevant convective frequency for those simulations. We've also plotted this with different domain sizes, which can be seen by the colors. So in all 3 cases here, we can see that when we're above the convective frequency, we obtain this -2 scaling in the effective viscosity in agreement with Goldreich and Nicholson. Also at the extreme low frequencies, which doesn't occur in the R/1000 case for computational cost reasons, we observe a frequency independent regime in both the R/100 and R/2 cases, which occurs at lower frequencies when the box size is larger. So the small domain sizes of 2 by 2 in the R/100 case, they are frequency independent at the convective frequency and lower. So the interesting part though is that when the domain size is of adequate size, so in the R/100 case 4 by 4 or larger, and in the 2 by 2 case 12 by 12 or larger, we obtain this significant -0.5 scaling law in the effective viscosity, which extends for about 3 decades below the convective frequency. So a question might arise as to, well, where does this come from? So if we consider just convection without the oscillatory shear, and we consider the spatial kinetic energy spectrum of these three different strengths of convection for the various domain sizes, then we observe that when the domain size is suitably large enough for that given strength of convection, then this minus 0.5 scaling manifests when the energetically dominant peak in the spectrum is able to exist in that domain size. So for example, in the R of 2 case, if we look at the domain size of 8 by 8, the peak is somewhat resolved, but the curve is not really following the resolved larger domain sizes. Once we get to 12 by 12, then we are properly resolving the energetically dominant large-scale modes, and therefore we get this minus 0.5 scaling. Similarly, for the R of 100 case, this can be seen by following the 4 by 4 and the 8 by 8 seem to resolve the peak well, but the 2 by 2 does not. So this tells us that essentially we need the large-scale modes in order to get this minus 0.5 scaling. An interesting thing about this, though, is that in the R of 2 case, we obtain in a high-frequency regime the minus 0.2 scaling of Goldreich and Nicholson. However, if you look at this spectrum, there is no Kolmogorov-like turbulent cascade here. This is a laminar flow. And the Goldreich and Nicholson prediction is based on the assumption of a Kolmogorov-like turbulent cascade in the flow. So this is quite interesting. So let's move on from this and consider if we just fix the domain size and choose different strengths of convection, what happens? Well, you end up collapsing everything on down to one master curve, but we get some scatter in a high frequency regime. So interestingly, this scatter can be explained by this insert where we denote the different shear amplitudes. So we're seeing that we're getting some shear amplitude dependence in the high frequency case, but interestingly, we do not get that in this intermediate minus 0.5 regime or the low frequency. So we've kind of said that we need the large scale modes to get this minus 0.5 scaling, but it doesn't really tell us much else about it. What we can then do is we can consider the frequency spectrum of the kinetic energy. So this is the temporal spectrum essentially. So this is in time. So this is fixed domain size of 8 by 8. So that's, in this case, we're resolving the energetically dominant modes. And just to note that because the shear is weak in all cases, this spectrum is not strongly modified in the intermediate and low frequency regime by the shear. So these are representative of what the frequency spectrum would look like for sheared cases. So what we do notice is that there is this significant region of the spectra that has a minus 0.5 scaling law. So that's quite interesting. So what we can do is we can then compare this frequency spectrum with the effective viscosity plot. So as an important note, the y-axes of both of these they're shifted but not scaled. So the number of magnitudes in each case is the same. So we've not just squashed these to make this look like it's good. This is actually just what it comes out as if you shift the axes. And what happens is you see that over the minus 0.5 scaling of the effective viscosity, this seems to coincide with the same frequencies of the frequency spectrum. So it seems that essentially what is happening is that the effective viscosity from low frequencies of frequency independent follows the spectrum, follows the minus 0.5 slope, and then leaves the spectrum following a minus 2. The point at which it leaves the spectrum is determined by the amplitude of the shear. So you can see this by following the squares and see that they fall off from the spectrum at a lower frequency than, say, for example, the triangles, which fall off at a higher frequency. So another point to note is that this is just one case. We've done this for quite a lot of cases and we get similar results. It's quite robust. So something else that's worth mentioning is that we can look at the spatial contributions. So what scales are contributing the most to, say, the effective viscosity, this nu E. This also has the Reynolds stress, but I've not had time to talk much about that. So for the effective viscosity case, essentially what we're seeing here is that we've got low frequency, intermediate frequency, and high frequency regimes top to bottom. And what we're seeing here is the contributions to the effective viscosity at what scales. So since these are all constrained to these small wave numbers, this means that it's the largest scales that are dominating the contribution to the effective viscosity. Okay, so this is kind of the key takeaways from this talk and also the 2 papers we've put out on this. Essentially, we have this low frequency independent regime. We have this new scaling law of minus 0.5 for an intermediate regime, which occurs below the convective frequency. So we now actually have to start considering that we're getting a reduction in the efficiency of the dissipation below the convective frequency. So this is kind of new. And we also find agreement with Goldreich and Nicholson in the high frequency regime. So in terms of what these represent in terms of models, the first one, the low frequency regime, that corresponds to a constant time lag model. And then the intermediate frequency regime doesn't correspond to any model anyone, as far as I'm aware, has ever used. And then there's the quadratic model of Goldreich and Nicholson, which people have used as well. Nowhere in this appears the constant Q model of Zahn, which we've not found any evidence for that existing. Another important point to make about this is, if we're considering a high frequency regime, because of the strength of the attenuation of the effective viscosity, we may want to be considering mechanisms such as the dynamical tide rather than the equilibrium tide as the primary mechanism for dissipation in those cases. So thank you very much.